Hi, this is Professor Iris Miano with Day 18 Math 2 lecture spanning 3 sections concerning graphing trigonometric functions. I'll waste no time. Let's get right into it. The first one that we'll want to introduce, other than noting that we're going function notation / the y equals whatever the trig function is of x, that's mainly the way that we'll be sticking to it. Okay, let's introduce the sine function first. We're going to limit our initial introduction to a domain from 0 to 2 pi. And we want to do this just so that we get to know some familiar key points here that you may recognize from unit circle. So there are some key features that we are concerned about in regard to being able to draw a sine function, and that's going to be anytime it crosses the x-axis, what are the values of its maximum and minimum areas, and also a couple of points in between so we can get an idea of being able to draw the curve nicely, okay? But we know that the domain of the sine function is all real numbers. So really when we graph these things, we can graph several different periods, several cycles over is another way that you can describe it. And you'll want to have the endpoints of your graphical representation have arrows generally so that you can clearly indicate to the reader that these trajectories go on forever and ever in this pattern. Here is an overview of the properties of the sine function, mentioning the domain, the range, the fact that the function is odd, which means it has rotational symmetry about the origin. Its period is 2 pi, which can be easily manipulated, as we'll see in transformations that we're going to cover. And here's a list of the x-intercepts. They happen at multiples of pi and 0. And the maximum values occur at these multiples of pi over 2, these other multiples of pi over 2, and more, of course. The minimum value occurs. Okay, moving right along. So, am I re-recording now? Sorry, I paused. There we go. Okay, so a natural next step for us will be talking about transformations, and they lend themselves to the way they've been initially defined for other parent functions back in section 1.5. So if that's something you want to review, it couldn't be a bad idea to do that. Here in figure 47, we see an example of a couple of transformations, one of which would be a scalar multiple of -1 in front of the sine function in particular, which flips over the sine function over the x-axis. It's just a mirror image reflection, and if we needed to, for whatever reason, adjust the period, we could compress it or stretch it. Here is an example of 1/2 compression on the period, making the original function's period of 2 pi reduced to a period of pi. Now, let's similarly define the cosine function. Let's limit our first look to the domain spanning 0 to 2 pi, so 1 full cycle. And notice that distinct from the sine function, we start up at a value of 1, and that's because the value when the radians are 0 in the cosine function, the output is a 1. And then we cross the x-axis at pi over 2, indicating a cosine value there of 0, have a valley or a trough at pi, cross again at 3 pi over 2, and then have another peak at 1 at the end of the cycle. And here are the corresponding ordered pairs associated with this figure as well. But we know that the cosine function, like the sine function, has a domain of all real numbers. So here it is in its entirety, or at least implied entirety, with arrow points at the end of those trajectories. Here's a list of all of the properties that were similarly defined for sine earlier, but for cosine: domain, range. This function's even. It has a period of 2 pi, just like the sine function, but the x-intercepts and the maxes and min values occur at different places compared to the sine. We could talk about manipulations of transformations, like if we needed to stretch it vertically, we can multiply it by some number. Here in this example, we have a stretch by a factor of 2. If we needed to horizontally compress, we would have the multiplier be directly on the x, and that would kind of compress it like you would folding in an accordion. Just a moment. Oh boy. No, I'm just gonna hold on. Can you see this window? Yes, I can. I've got to pause you. Okay, it looks like we can continue. You may notice that sine and cosine look very much the same, and in fact the parent function waves are exactly the same in period and the maximum and minimum values. It's just that the cosine function is a pi over 2, a horizontal shift away from the sine function. So you could do a horizontal shift, also known as a phase shift. We'll get deep into this in section 5.6 at the end of this lecture video, as we see here. Okay, so there's lots to cover. I'm just going to go ahead and kind of breeze through some of these things, and being able to tell you about various manipulations here. So here's another example of a vertical stretch by a factor of 2. It's a multiplier of 2 out in front of the cosine function now. And if we want to do vertical stretching, we could do so by virtue of this coefficient in front of, or multiplier rather, in front of either the sine or the cosine function. It's also called the amplitude, which is defined formally in just a little bit. Furthermore, if we needed to compress or stretch the period itself, like how the sine function either is stretched or compressed horizontally, we could do so by changing the period. And so that has algebraic representation right here in this yellow box, okay? So the amplitude is defined as the absolute value of the multiplier in front of the sine or cosine function, whereas the period is defined as 2 pi over the coefficient in front of the x, directly inside of the, hold on just a moment, directly inside of the sinusoidal function. Okay, so now we have all of the elements that we need. We can talk about graphing these sinusoidal functions using a 4-step process as determined here in this yellow box, which I will allow you to read on your own. I'm going to go through the process, of course, through example. I'll spare you the details of reading the summary for you. I do want to practice with you now finding the amplitude and period of equations of cosine and sine functions. Let's start with the number 14. And you can see out in front we have of the cosine function, there's a factor of 3. That is your amplitude. So a equals 3. That was easy, right? Found the amplitude straight away. And the coefficient in front of the x is a 1. That's your omega. Now, in order to calculate the period, you have to take your omega and divide it into 2 pi. That's supposed to be a pi right there. But your omega here is 1. It's a pretty silly thing to do. Here, the period is still just 2 pi. Okay? No period change on that particular cosine function, but we did have an amplitude of 3, which we'll do a vertical stretching. All right, moving on to number 16, notice that we have a multiplier in front of the sign of -1. That would be our a value, but remember when you always take the absolute value of the multiplier out in front, so that means your a value is actually a 1. And here we'll actually need to do some work and recognize that omega is a 1/2. So the period is equal to 2 pi divided by that 1/2. Well, put your algebra hat on. Whenever you divide by a fraction, you actually multiply by its reciprocal. So that makes the period here 4 pi. Number 20, we have a multiplier in front of our sine function of 4/3, so just plop that down as your amplitude. Done deal. It was already positive, so we didn't need to take the absolute value of it by any means, and then take the coefficient in front of your x term of 2/3, define that as your omega, and then to find the period, take that omega of 2/3 and divide it into a 2 pi. When you divide by a fraction, it's the same as multiplying by the reciprocal. Those 2's will therefore cancel, and you have a period of 3 pi. All right, moving right along, let's do some matching. You will see an exorbitant amount of graphs here, sinusoidal, so sine and cosine graphs here of amplitudes ranging from 2 to 3, and depending on the sign of the multiplier in front of your either cosine or sine function, that'll determine the look of and positioning of either the y-intercept or the movement from the y-intercept over to the right. In any event, let's just go ahead and relatively quickly match up all of these graphs to numbers 23 through 31 equations. So for number 23, we have a sinusoidal with a positive 2 multiplier out in front, so it's going to have an amplitude of 2, and it's going to move up from the origin in its movement to the right in the positive x direction. We have, by virtue of an omega of pi over 2, a period of 4. So a sine function, period 4, amplitude 2, that is f, okay? For number 24, we have a cosine, amplitude 2, also a period of 4. That's looking like E, my friends. For 25, we have a cosine, period of 2. An omega of 1/2 means that the period is 4 pi. Which one of these has that those features? Well, graph in part A. 26, we have a cosine with an amplitude of 3 and a period of pi. That is I. For 27, we have a sine with an amplitude of 3, but it goes down as you move forward in the x direction from the origin, and it has a period of pi. That is looking very much like H. Number 28, we have a sinusoidal with a positive 2 multiplier in front, so amplitude of 2, omega of 1/2 means that the period is 4 pi, so that's going to be B. Almost done here, folks. Stay with me. We have a cosine with a amplitude of 2, but it starts at -2 on the y-axis, and an omega of 1/2 means that the period is 4 pi, so that is looking very much like C's graph. A cosine, again, with a -2 multiplier, so that's an amplitude of 2, but it starts at -2 on the y-axis. Pi over 2 omega yields a period of 4, so that is looking like G. All right, sinusoidal, so a sine function, amplitude of 3, period of pi, that is J. And then lastly, a sine that slopes down from the origin, amplitude of 2, period of 4 pi, that is very much D's graph. Okay. Cool, so hopefully everybody was able to follow that, even though we went through it relatively quickly. Now let's go ahead and actually graph some stuff. So here we go. The first thing that you'll want to do is note the amplitude, which is 1, and the period, which is going to be 2 pi over the omega here is 3. And we want to come up with 5 ordered pairs, which are going to give our 5 key points. So since it's a sine function, we know that the inputs are going to range from 0 to, well, whatever the end of the period is, which is 2 pi over 3. okay? And then we'll have 1 point in the middle that's exactly halfway in between. So what's halfway between 2 pi over 3 and 0? Well, that would be pi over 3. And then halfway between 0 and pi over 3 would be pi over 6. And then halfway between pi over 3 and 2 pi over 3 would be pi over 2. Now, how did I do that so quickly? Well, I did the work ahead of time. So you could just write that down and follow along with me and trust that that's what's up. Okay, now at the beginning, we start at the origin for a sine function that doesn't have any horizontal shifting to it, or vertical shifting for that matter. And we know that we end at 0 as the output. And then here, right in the middle, we also are going to cross the x-axis, and so our y will be 0 there. At this very first key point, halfway between x-intercepts, we know we're going to have a maximum. And why do we know that? Because that's something that's indicative of the sign, which doesn't have any negative amplitude multiplier out in front. So that means we're going to have a value of 1 right here, okay? And then at this, after we cross the x-axis, we're going to have a minimum, which is going to occur at negative 1. So those 5 points are going to need to be graphed. And so here is the graph of those 5 points. Here's 0, 0, pi over 6, 1, pi over 3, 0, pi over 2, negative 1, and then 2 pi over 3, 0. So go ahead and draw a curve which starts here, goes up, and try and make it as smooth as you can. And the first couple of times they're not going to look so great, and that's fine. You just want to avoid making straight lines from point to point. You want to try and make it curvy. Now I cheated and used a graphing utility so that my curves would look really good, but this is basically how your sinusoidal curve should go for this first graphing example. Okay, so notice that all of my curvy bits go through the one full cycle, and then draw at least another cycle after that using the same curved pattern, and then you've done it. You've done exactly what you need to do in order to get through this graphing problem. Okay, let's try one more example, but with a cosine, and let's make it a little bit more complicated. We're going to have a vertical stretching in addition to a period change. So notice that the amplitude is 2 here. We'll take that into account. And the period is 2 pi over 1/4, which if you take 2 pi and you divide it by 1/4, then that means your period's going to be 8 pi. So it's going to take a distance of 8 pi for the curve to travel in order to get through one full cycle or one full period. Furthermore, we need to come up with what would be our key points. So draw yourself room for 5 ordered pairs. You know that since it's cosine, you're going to start at, and it's positive multiplier out in front, you're going to start at your peak. So as far as the output's concerned, so that'll be a 2 here, and you're going to end at your peak as well, which will give you a 2 there. And for the place in between, you're going to go to your trough or your valley, so that'll have an output of -2. And then these places in between, your outputs will be zeros or x-intercepts. Okay. Then you know that you're you're going to start at an x of 0, and you're going to go all the way out to your 8 pi. So that's goes straight here no matter what. Definitely whatever the value of your period is, that's going to be the x value of your last ordered pair for your 5 point summary. And then, or your 5 key points rather. And then you got to go halfway between that here, and then halfway there, and whatever the halfway distance from 4 pi to 8 pi, in this case it'll be 6 pi. Okay, so that gives you your 5 key points. So here now we can plot them, and there they are. And we want to envision starting from 2 and then kind of slowly curving down, crossing there, curving back around up here, crossing the x-axis there, whoops, and then looping back up, and then continuing on in that same pattern with the same amount of same crossings in the same relative positions. So what will that look like? Well, that's what it will look like. So there is y equals 2 cosine 1/4 x. All right, cool. Now let's go ahead and do 2 more examples from this section in which we are going to just take the amplitude and the period of a of an yet to be written equation and come up with what the sine function would have to look like for that. Well, if your amplitude is 4, then that's going to be the multiplier out in front. So we can go ahead and start this off and say that it'll equal y equals 4 sine of what? What goes inside of the sine function? Well, it's going to be something other than just x, because we definitely have a period other than 2 pi, right? So this is your p-value. So kind of work backwards here and say, all right, well then p has to equal 2 pi over omega. Well, omega is whatever, that's going to be your coefficient in front of the x inside of the sine function. So if p equals 1, then omega has to equal 2 pi, right? That's the only way that this ratio is going to equal to 2 pi. So therefore, your coefficient in front of the x is going to be a 2 pi. For y equals 4 sine of 2 pi x. That's going to be the equation. Okay, last example for this section. Let's find the equation of this function just by looking at the graph. So a couple of things you'll want to notice right away is that at x equals 0, the output is at what I would call the amplitude, but it's at the negative version of the amplitude. So for that reason, I would say that the multiplier in front of my trigonometric function is going to be negative for sure. And since we start in a place other than at the origin, it's going to be a cosine. So I see that the multiplier is negative 5/2 on and I'm going to call it a cosine. The next thing I'll need to see is what the period is. Well, from trough to trough, that gives me the period. So I can see that the period is 2. Okay, so period equals 2. That equals also 2 pi over omega. I can solve for omega in order to figure out what the multiplier is in front of this x right here. That's going to be what I put right there. And looking at this, just this part of it, that is, what does omega have to be in order to solve this equation? Well, it's got to be pi because it's got to cancel out with this pi up here. So that means omega equals pi. So that'll be having an equation of y equals negative 5/2 cosine of pi x. Cool. And that is our first section. 2 more to go. Let's hit it. Okay, so now we are graphing tangents, cotangents, cosecants, and secant functions. We're going to introduce the tangent and the cosecant the tangent and the cotangent rather, similarly to how we introduced sine and cosine. Let's just look at a piece of it, at least for the tangent, spanning our domain restricted from negative pi over 3 to pi over 3. So as you can see, a few key points are plotted, so you get an idea of like the shape of the curve, but these trajectories beyond pi over 3 and negative pi over 3 continue forever, but they do ride asymptotes. So as I scroll down, you'll see that this curvy trajectory indeed does follow asymptotes at multiples of pi over 2, and the trajectory repeats itself patternistically every period of pi, right? So the distance between asymptotes is it's got a width of pi. And from what we could see from this table, you could see how there's the instance of the asymptote here at pi over 2, where the output is undefined because the cosine, the denominator value in the ratio version of tangent x, which is also defined as sine x over cosine x, at pi over 2, the cosine of x is 0, so that means that the value of the tangent is undefined there. Hence, the placement of these asymptotes. Here is a little list of the properties of the tangent function, so you'll note those, particularly when you're trying to graph a tangent function. Domain and range is listed here. So it's an odd function, so it has rotational symmetry about the origin. Its period is pi. X-intercepts are listed here. It's a non-exhaustive list. It has a pattern to it. And the y-intercept at 0 is displayed. And then the position of the vertical asymptotes. They occur at pi over 2 multiples. Okay. So the way that we talked about sine and cosine in regard to transformations, similar things can be said here about tangent. If we have a vertical stretch by a factor of 2, an amplitude of 2, then that means that some of the position of a couple of the key points changes. It gets like shifted, upwards by 2 as far as the output's concerned. Now, if we have some this is a vertical shift downward by 1, because that subtracted off 1 is outside of the tangent function, then that just pushes everything downward. Okay, now if we had some manipulation directly on x, then that's going to change the period. So not only do we have a vertical stretch by 3 in this example for figure 65, which changes, of course, the vertical positioning of a couple of these key points. It also changes their horizontal positioning by virtue of changing the period to pi over 2 in this case. Okay, cool. Here we are going to, relatively similarly, but with a little bit less information, define the cotangent, which you may notice is looking very much like the tangent. Instead of increasing over its period, as you move from left to right between the asymptotes, the cotangent decreases, and it is shifted over compared to the tangent, whereas the tangent goes through the origin. The entire y-axis is an asymptote for the cotangent. So the asymptotes are in different positions, and the shape of the curve is opposite compared to the tangent function. Okay, so when we plot the secant and the cosecant, we also plot them with their cosine and sine counterparts respectively. And that's just to make it easier to figure out where the asymptotes lie and the positions of the vertices for the parabolic shapes that are exhibited by the cosecant is what you see here, what I'm hovering over with my mouse. And then down below we have a secant plotted in blue. So cosecant and secant are in blue for figures 67 and 68 that you see here. And then their sine and cosine counterparts respectively are plotted in black. Okay, so yes, they come in pairs. Now there's two different ways to think about plotting them, particularly when we're talking about instituting transformations. One school of thought is to plot the parent function with its corresponding parent sine function, and then transform just the blue stuff, which is the cosecant, for instance, here. So they plotted their cosecants, and then they just moved around the cosecants according to the transformations, which for this one was vertical stretch by 2, so the vertices move up to 2's and negative 2's instead of 1's and negative 1's, which are the, the usual troughs and peaks of the original parent cosine function, or rather sine function, which is the counterpart for the cosecant. And then also subtracting by 1 for the entire function, it just shifts everything down. Or rather than that, you could do like what they did in figure 70, which is to perform the transformations on the counterpart function, which for the cosecant would be the sine, and then draw the little parabolas on the troughs and valleys of the already transformed sine function. That's what I would recommend that you do personally. I'm more of a figure 70 type of gal, so that's what I'm going to demonstrate. Okay, and here we go. We're already ready to graph some functions. And so I'm going to draw you a tangent function with a multiplier of -2 out in front. Okay, so what does that look like? Well, we need to recognize that the amplitude is 2, so we can say, oops, let's get that going. The A is 2. Yeah, we don't even need that actually. We do not need this. You know what we need to do? We need to come up with our 5-point bit and determine what will be the position of the hold on just a moment, the asymptotes. Okay, so we didn't change the period at all with this tangent, so the asymptotes and the crossings of the x-axis are going to be in all of the same positions there. Okay, so here are the five points we're going to want to keep in mind. Obviously, you want to have your pi and your negative pi, because we want to do 2 full periods, 2 full cycles, and we want to go the origin in between, and we want to recognize that actually there's no, hold on just a moment. Sorry, we want to have these are going to be where they cross the x-axis, there and there, and then these positions, these are going to be akin to these critical points here. Sorry, let me just scroll back to the tangent. I got myself a little bit turned around with this stuff. Oop, there we go. So we're talking about these right here. I'm going to go ahead and circle them. These points are the ones that we're going to want to manipulate according to the stretch factor of -2. So it's going to be kind of flipped over the x-axis as far as this trajectory is concerned. For our -2 tangent x, it's going to be going in this position, and instead of going up at pi over 4 and negative pi over 4 to either 2 or -2 or 1 or -1, it's going to go to 2 or -2. Okay, all right. Let's go ahead and finish this up. Sorry. So for these 2 intermediate points in between, we're at negative pi over 4 and positive pi over 4. And we'll go up to positive 2, right? Because we would normally be at -1 here, but we're going to multiply it by a -2 to get a positive 2. And then it'll be a -2 here, because in the parent function, so just to be clear, I'm going off of the parent function having the points negative pi over 4 negative 1 involved, and also pi over 4, it goes up to a 1. So multiplying by the factors of negative 2 here and here, that's how I'm getting the positive 2 and negative 2 respectively. Okay, let's go ahead and actually show the position of these 3 points right here, and also we have vertical asymptotes. I forgot to mention that, and now I'm showing it to you. Vertical asymptotes at multiples of 2 pi. Of pi over 2, rather. Okay, so that's what these green dashed lines are. So here I have plotted, here's 0, 0 right there. Here is pi over 4, negative 2. Here's negative pi over 4, positive 2. And here is negative pi 0 and pi at 0, okay? And then I have a couple of extra points within each other set of asymptotes where I know that they will be in the relative position according to the pattern that's already been established. So then I can go ahead and draw my curves that go through those points, and I have in blue my tangent, a negative 2 tangent x. Okay, cool. So a lot of assumptions that are being made about the positions of certain points in here, so you really need to get to know the parent function of tangent x and then make adjustments accordingly. Okay, let's go ahead and have a cotangent example next. And this time we're not going to have a multiplier out in front, but we are going to have a period change. The period is no longer going to be pi, in which the parent function has that period of pi normally. Here we're going to have to say the period is going to be pi, whatever the old period was, over omega, but omega is pi over 4, right? So this means that the new period is therefore a 4. So we'll keep that in mind. So that means that now 4 is going to be the multiple at which the asymptotes occur. So this is indicative of the cotangent. So this is something that you may not have known initially, but 4, so asymptotes occur at x equals 0. My bad, guys. Hold on. X equals 0, aka the y-axis, and at multiples of 4. So we'll keep that in mind. Now let's get at least a few of the what's it called? Points plotted. So for the original parent cotangent, we can expect to have the following points of pi over 4, 1, pi over 2, 0, and 3 pi over 4, negative 1. So these occur within one cycle, right? But if we need to make adjustments for this period change, so I'll just draw some arrows and say via period change, this is how they'll be now. So this point will correspond to a 1, 1. So whereas like pi over 4 was the first piece of being broken up into 4 pieces of a period of pi, since the period is of 4, we need to divide by 4 to get this first corresponding point. And then we will go to, divided by 2, or sorry, go halfway. So that'll be a 2, 0. And this one will correspond to a 3, -1. Okay, so we can plot these 3 ordered pairs along with all of the asymptotes, and then also some more ordered pairs that follow the same pattern. And this is what they'll look like. So just to be clear, these are the 3 points that I plotted. Here is 1, 1 right here. Here is a 2, 0, and here is 3, -1. And then notice that I have a vertical asymptote at 0, or x equals 0 rather, x equals 4, x equals -4. And I could have done more, but it's a little bit out of the window. So go ahead and draw your curves now, following those asymptotes and going through those points, and you will have your cotangent of pi over 4x in blue. Okay. Couple more graphs to go. Now let's switch gears over to a cosecant, which is the reciprocal function to the sine. So first we're going to graph the sine counterpart, which will be graph also y equals 1/2 sine of 2x. Because that's the easier part. We can do that first, and then we'll just notice the peaks and the troughs, draw parabolas on them, and figure out where the asymptotes go, and then Bob's your uncle. Okay, but first, let's come up with some things here that we need. First, we need the period. Well, we need to recognize the amplitude is 1/2. Cool, we'll note that. And then the period equals 2 pi over 2, aka pi. Okay, so the period is now pi, and so the key points that we want to draw for the sine counterpart will be the following. Oh, we need a 5th one. Hold on, let me make some more room. Okay, so we have no vertical or horizontal shifting, so we know we're going to start at 0, 0. And the fact that we have a now period of pi, we're going to end at pi 0. And then that means we're going to have the in-between parts are going to be at pi over 2, pi over 4, 3 pi over 4, because remember all of these little points need to be the same distance apart. That's supposed to be a 4. Okay, and then the scaling of 1/2 makes it so that the maximum value, which occurs at this first yet to be completed point of 1/2, and then a minimum value occurs over here at -1/2, and then of course we cross the x-axis again at a pi over 2. Or halfway in between the period. Okay, so let's first plot, okay, sorry. And these, okay, so these are your max values, so this is going to be a vertex. So for, now we're getting into the territory of the actual, oh crap, hold on, I got a battery low situation. Okay, I'm going to assume that you guys can still hear me. I just had to plug in my headphones. Okay, so where were we? So now in regard to, let me get that out of the way. We're talking about the asymptotes and the vertices. So this is, let me erase that real quick. So these will be your asymptotes, will be at 0 and multiples of pi over 2. Asymptotes are happening here and there and there, and then that'll be a vertex, and this will be another vertex. Okay, so I think we have everything outlined here that we need. So the first step will be plotting the critical points, those 5 points, and then also the asymptotes will be in green dashed lines. Okay, so Yes, so we're using the information at 0, 0, right? So it's like that'll be a crossing for the sine function, certainly. And but every time the sine function crosses, that'll be acting as an asymptote for the reciprocal function. Okay, because obviously if the output is going to be 0 for the sine, then the reciprocal of that is going to put the 0 in the denominator position, and that's going to be not able to be graphed in the coordinate plane. Okay, so here is the sine function in blue. Okay, so this represents, and let me go ahead and get a blue thing going here. Blue. So this is, I'm going to circle it in blue to say that it's the sine function, and then the cosecant, I'm going to show you in just a second, that's going to be a parabolic trajectories having vertices at these green dots, the peaks and the troughs, and they're going to be using these green dashed lines as asymptotes, like so. Isn't that beautiful? Okay, so in purple now I want to circle the cosecant function so that we can make that connection there. Okay, whew. Yeah, it's a lot of work. It's not for the faint of heart here. All right, let's move on to one more example from the section, and then we're going to wrap up with phase shifting, and we're only going to graph one more example after that, and then we're going to have one more, just more algebraic example. Okay, the secant. Now, the counterpart there being the cosine, right? So we're going to also graph. Oh, hold on. I'm going to go back to my hot pink here. So also graph y equals 3 cosine 1/4 x plus 1. Whew. So we do have a vertical shift here by 1. Nothing we can't handle though. So let's go ahead and note some things. Our amplitude is 3. Our period is 2 pi over 1/4, which is 8 pi. And we're going to do this in a couple of phases. So what I would recommend that we do is maybe just for in green here, we're going to just focus on this bit right here. And then we're going to shift up by 1 for the output. Okay, so if we're just dealing with this first part, ignoring the plus 1 for right now, what would be our 5 ordered pairs that we would care about? Now, these are not the ones we're going to plot. We're going to actually plot the ones that have the vertical shifting up by 1. I just think it's a little bit easier to think about it this way first. Okay, so we're going to have an output of 3 to begin with, because we have this multiplier of 3, and then we're going to end with an output of 3. Okay, and then we're going to go down to -3. All right, because that's what cosine does. It goes to its peaks on the outer edge, and then it goes to a trough in the middle. And then in between, we have these zeros, right? Okay, as our outputs. Cool, cool, cool. We're going to shift those up by 1 in a second. Now, let's use our information about the period to break this up into pieces. 0 to 8 pi, we're going 4 pi here, 2 pi there, 6 pi there. Okay, so that's if we're just doing this first part. I don't know why, but it's better for me to just do it in pieces. And then let's go ahead and account for this plus 1 now by doing a plus 1 on all of the outputs. If you're like, I could do this on the way, I don't need to do this extra step, by all means, do you, honey, okay? Do you. So now I'll have as my ordered pairs 0, 4, 2 pi, 1, 4 pi, -2, 6 pi, 1, and 8 pi, 4. Okay, let's check my notes. Yes, that looks good. So again, for the secant, because of the nature of it being lined up with the cosine, these ones are going to be your, which ones are going to be your asymptotes? Asymptotes are going to be here and there. It's a little bit opposite compared to what was going on with the cosecant. And here's a vertex, another vertex, and another vertex. So let me go ahead and show you some asymptotes and these. So the asymptotes are going to happen at 2 pi, 6 pi, what would be 4 more pi after that, right? So here's 2 pi, 6 pi, 10 pi, 14 pi, 18 pi, okay? And also you can go back for -2 pi, cool. And then here are my vertices. I have one at 0, 4. I have one at 4 pi, -2. I have one at 8 pi, +4. And then I continued on with the pattern with these additional points right here. Okay, so here in the next step, I'm going to show you the cosine, which is in blue. So let me go ahead and circle this in blue. Oh, let's try a blue that's a little bit closer. So that's going to be this guy. It's graphed in blue. And then in purple, I'm going to draw the actual secant, which is going to be, again, sinusoidal, or sorry, it's going to be quadratic, looking like parabolic elements that have vertices at these green points, and they're going to be writing these asymptotes, the green dashed lines, which look like what you see here in purple. Okay, yep, so the purple bit is the actual secant function, but we used a lot of elements from the corresponding cosine function in order to draw it. Okay, whew. So yeah, have fun with all that. Okay. Last section, we'll wrap things up here relatively quickly. We just want to talk about phase shifting. I know that this section also covers sinusoidal curve fitting, but that's not something that I want to get into in this class. You'll have plenty of time for that in your next level class, so don't worry about it. It's going to get covered in your mathematical journey. So phase shifting is basically just horizontal shifting, and it has a bit of algebraic flair to it. By which I mean, if you're going to shift over your sinusoidal function a distance of phi over omega, we're getting real Greek with it, then the amount of value that you subtract from your omega x inside of your sine or cosine function is going to be phi, okay? So you subtract off phi, but that's a shift horizontally of phi over omega. So it's definitely super confusing that those are not the same exact thing. You have to account for the fact that there's this factor of omega in there that kind of gets, for lack of a better word, factored out when you think about it as being a horizontal shift, okay? So if you remember what was up with horizontal shifting in other parent functions, then hopefully this is going to make some sense to you, okay? So let's go ahead and add the phase shift ratio of phi over omega to our cache of elements that we use in order to plot sine and cosine graphs. And it's just now one more step in a process that has already been presented. So here is a basic summary, blah, blah, blah. I'll let you read that on your own time and get straight to a demonstration of a particular sine function that I want to graph. Okay, so this is a sine function with an amplitude of 2. So let's go ahead and mark that. A equals 2. The period is 2 pi over 1/3, which is 6 pi. And so now we get to deal with this little bit right here. This pi over 4 is our phi. but that's not the phase shift. The phase shift is pi over, or sorry, phi, not pi, phi over omega. And what was omega? Omega was 1/3, right? Let me just go ahead and omega. There we go. So therefore the phase shift is pi over 4 over 1/3, which, get your algebra hat on, that's going to be 3 pi over 4. And this is where it can get a little bit complex. So I'm trying to figure out what the good 5 points are that you need to come up with. So what I like to do is to look at, and I'll do it in green so it just kind of is contrasting to what was going on over here. Like, we need all this information, yes, cool, but I want to just draw a much simpler version of this where we don't have any vertical or horizontal shifting yet. I want to do that in a subsequent step. So I'm going to first fiddle around with 2 sine of 1/3 x. Okay, so the period is still 6 pi. I'm definitely going to keep that, and I have a vertical stretching of 2. Cool. So for that, my 1, 2, 3, 4, 5 ordered pairs would be the following. Okay, so I'm definitely starting at 0, 0. Cool, I know that. And the end of my first cycle is going to be at 6 pi 0. All right, so I know that I'm going to go 3 pi and 0. I'm going to cross the x-axis again in the middle. I'm going to have a, what's it called? A peak and a trough. So here's my trough, and since my I got stretched by 2, it's going to be an output of -2, +2 here, and I got to break up my 3 pi in half, so it'll be 3 pi over 2, and this will be 9 pi over 2. How did I do that so quickly? I did the work ahead of time. That's the halfway point between 3 pi and 6 pi. Okay, you got to go another 1.5 pi's, and yeah, okay, so I'll just let you guys figure that out. So that's going to be the 5-point summary for this much more simplified version. But, you know, we have some vertical shifting by going up by 5 here, right? Up by 5 here, and then also we have a phase shift of 3 pi over 4. So how do we account for that? Well, basically, and I'll do this in another color here, for every x value, you're going to increase it by 3 pi over 4, plus 3 pi over 4, plus 3 pi over 4, plus 3 pi over 4, right? This is the slow and careful way, and that's what I like to do. And then I'll switch the color one more time even and say, okay, now we got to deal with the vertical shifting, which will be increasing it by 5. So plus 5 here, plus 5 there, plus 5 there. And if you write all this out, I feel like the next steps are just much more simpler. Okay, so then your actual 5 ordered pairs that you want to grab and plot become this, right? So we'll just put little arrows. Okay, so this will be 3 pi over 4, 5. This will be 9 pi over 4, 7. 15 pi over 4, I know, that's getting crazy, with a 5. 21 pi over 4, with a, what was that? With a 3, excuse me. And lastly, 27 pi over 4, with a 5. Okay, so let's plot these 5 points, and what will they look like? That'll be these guys right here, okay? Yep, there they are. So let me just scroll this down a little bit so you can see the ordered pairs, and here they are. So yeah, it's a little bit jarring to try and plot them, especially given the scale that I've provided you with. It's not super easy, but just, you know, do your best to round these, and they're in terms of pi. So for instance, if you want to estimate 15 pi over 4, well, 15 is pretty close to 16. 16 divided by 4 would be 4, so this is pretty close to 4 pi, and indeed, that's where that ordered pair is. About 4 pi, but a little less than, and at 5. Okay, so now we can come up with the sinusoidal curve that fits through there, and then continue the pattern. And there it is, okay? So yeah, there you have it. There's a lot of work beforehand before you actually draw your curve, but you know, once you're very confident about the positions of peaks, valleys, and what would be equivalent to crossings if there weren't any vertical shifts, then you can be sure that you are about to draw your sinusoidal curves very cleanly and nicely. Okay, one last example. Let's say, and it's an algebra one, okay? Let's write the equation for a sine function that has these characteristics. So the amplitude is 3. I can go straight away into saying, all right, it equals 3 sine something. But what goes inside, right? And that's wherein the challenge lies, okay? So if the period is pi over 2, okay, if that is your period, well, that is equal to 2 pi over omega, right? So you can do the cross product if you so please, and solve it, and you will find that omega equals, that's supposed to be a W looking thing, a 4 right there. Or you could say to yourself, oh, what does W have to be in order to give it an equivalent value to pi over 2? Well, that would be 4. Okay, so then that's going to be the multiplier in front of the x, 4x. And then there's an extra part to it because we do have a phase shift. So the phase shift, 2, is equal to phi over omega. Now, we already calculated omega as being 4, so that means that 2 equals phi over 4. So that means phi has to equal 8. And it's positive. And so when you have the structure here with a phase shift, you're always subtracting off the value of phi, which in this case will be 8. And there you have it, folks. Whew, we did it. Yikes. I'm sure you're going to want to see plenty of demonstrations in class. Let me know what they are when I see you then. Bye, guys.